This lab, we're not going to use the report sheet in the lab manual. We're going to do some additional things, and there's not enough space for those. And so the molecules I'd like you to do right now are, did we do ammonia? I can't remember. Back in, no? Okay, we're going to do ammonia, ammonium, and amide, NH2 minus. So can you draw the Lewis structures? Do you guys remember how to draw the Lewis structures, pretty much? It's basically the same as Chem 4, except we'll look at some more complex structures. But what we do when we do these is first we draw the Lewis structure, and then we determine the hybridization. And so I'll do ammonia here first. So if we do ammonia, NH3, I'll draw the Lewis structure. Which will look like this. What's the Lewis structure? And then I look at the shape. Do you guys remember Vesper? If we do the shape of this is not T-shaped like that. We have a lone pair here. It's going to have this shape here. And then the next thing is we have to have 4 orbitals in a tetrahedral arrangement to accommodate the electrons. Now, what orbitals are we going to have that are in the tetrahedral arrangement? So let's take a look at the orbitals we have so far for nitrogen. For nitrogen, we have 1s, 2s, 2p. Now, how many electrons does nitrogen have? 7. So we go 1, 2. Now it has 7 total electrons. How many valence electrons does it have? So it's going to have 2 core electrons and 5 valence electrons. That's normally what it has, 5 valence electrons. But sometimes the number of valence electrons can be more or less. For example, in ammonium, nitrogen doesn't have 5 valence electrons. In ammonium, nitrogen has 4 valence electrons. And in amide, nitrogen has 6 valence electrons. And it's because of this formal charge. That formal charge goes on nitrogen. So if nitrogen has a positive charge, that means it's got fewer electrons than normal. If nitrogen has a negative charge, that means it has more electrons than normal. And so if we compare ammonia to something like ammonium, ammonium has a positive formal charge on the nitrogen because it's missing an electron. Over here, this nitrogen has 1, 2, 3, 4, 5. That's normal. Over here, this nitrogen only has 1, 2, 3, 4. 4 electrons is 1 less than its normal valence. And so when we fill this, we look. Now, when we fill this, okay, we go 1, 2, 3, 4, 5. So this looks right. In fact, we could use the unhybridized atomic orbital energy level diagram here, and it would work, except the bond angles would be, now the angles between the p orbitals, what are the angles between p orbitals? Well, the p orbitals, we have 3 of them, and do you know what the angles on the p orbitals are? 90. We have 3 orbitals at 90 degrees. Now, when I look at this, I have 4 orbitals at 109 degrees. Tetrahedral is 109 degrees. So there's a mismatch here. If nitrogen were to have an S and then these 3 P's, then the angles are all wrong. And so what we have to do is we hybridize it to minimize the repulsion. So what we're going to do is we're going to take the S and the 3 P's and hybridize those to make hybrid orbitals. And the hybrid orbitals, we're going to come up with 4 hybrid orbitals from those 4 unhybridized orbitals, and those are going to be sp3. And since this is in the second shell, we'll just call it, or n equals 2, we'll call it the 2 sp3. There's 4 of those. The 1s are still there, unhybridized. And now we'll fill it in. We have 1 lone pair and then 3 singles. Here's my 1 lone pair here and then 3 singles. The 3 singles can bond to the hydrogen. And so what can happen is this. Hydrogen can come over here and we'll bond a hydrogen here, another hydrogen here, and another hydrogen here. When we bond those hydrogens to the nitrogen, this would be nitrogen here. What orbital on hydrogen is bonding? And so we'll take a look at this from hydrogen's perspective. When we look at hydrogen, hydrogen is simple. It just has a 1s, and it just has 1 electron in the 1s. I'll put the 1 electron in the 1s orbital spin down. And so that's this electron here. This electron's coming from the 1s orbital on hydrogen, like this. All right, now I'm going to try to draw the orbitals on nitrogen. So here I have the nitrogen, and I'm going to draw 4 equivalent sp3 orbitals in a tetrahedral geometry. So I'm trying to draw this orbital coming out of the board and this orbital going into the board here. Now I'm going to fill these orbitals with electrons. So in one of the sp3 orbitals, I have a lone pair. And so I'll just put that on the top here. There's a lone pair. In the other 3 sp3 orbitals, I just have the single electron like that. And then hydrogen's going to come in with its 1s orbital. 1s orbital is unhybridized here. And it's just going to be the spherical 1s orbital. I'm going to write this spin down. And then another 1s orbital over here from hydrogen. And then one back here. From hydrogen. Just write that spin down. So we have the unhybridized atomic orbital energy level diagram, and then we have this one. This is atomic orbital energy level diagram with hybridized orbitals here. Now there are 2 ways that we describe a bond. So we go from atoms. Atoms are going to have atomic orbitals, unhybridized initially. And we either use these as is, or we hybridize those to get hybrid. Atomic orbitals is often abbreviated AO for atomic orbital. So we can go 2 ways from here. So there'll be 2 branches. One branch is the easy way. It's easy, but not as accurate. We easier path. And this easier path is called valence bond theory. And the valence bond theory is a simplified quantum mechanical approach. In which a bond is equal to the overlap of atomic orbitals. And so when we create a bond here, I'm overlapping this sp3 on nitrogen with the 1s on hydrogen. And what that does is it increases the electron cloud distribution here in this region. This is what we call the internuclear region. The internuclear region is if I draw an axis from the nucleus of the nitrogen through the nucleus of the hydrogen, then I see there's overlap in this region here. This concentration of negative charge density here is going to mean that the nuclei are going to be attracted to this, nuclei being positive charge regions. And so that's what's going to hold the atoms together. And so a bond is equal to the overlap of atomic orbitals. The other path we could take is a harder path. And the harder path is called molecular orbital theory. This is a rigorous quantum mechanical approach. So, for example, in the simplified quantum mechanical approach, we don't get energies. So we can't calculate or predict what the spectrum is going to look like. That is, we can't calculate the wavelength of light that's going to do this transition or that transition because it's overly simplified. The advantage of valence bond theory is you could do it with pencil and paper. With molecular orbital theory, the calculations become very difficult. But, from this, we should be able to get the energies so we can take a look at what the spectrum should look like based on the theory, etc. And so we get more information from molecular orbital theory than we do from valence bond theory. But valence bond theory is a lot easier. And therefore, these aren't really competing against one another. These are complementary. Sometimes you don't want to do the rigorous approach. And this is good enough. Other times you need to do a more rigorous approach. So it's complementary. It's just more tools applied to this. And therefore, molecular orbital theory is a comprehensive, rigorous. Valence bond is not. So we can get rid of valence bond entirely and just go with molecular orbital, but it would just be too much to treat everything using molecular orbital theory. What molecular orbital theory is this. We're going to take our AOs, and then we do something in quantum mechanics called an LCAO to get our MOs. LCAO stands for linear combination of atomic orbitals. When we do a linear combination of atomic orbitals, this is in quantum mechanics, we generate these things. These things that are generated are molecular orbitals. Molecular orbitals are entirely new set of orbitals. So far, what have we learned? The unhybridized atomic orbitals would be the S, the P, the D, the F, etc. And so we have the unhybridized orbitals. Then we came up with these hybrid atomic orbitals. What are the hybrid atomic orbitals that you know? The SP, the sp2, and the sp3. So what we're going to do is we're going to take the atomic orbitals that we generated, whether they're hybridized or unhybridized, and we're going to do a linear combination of these atomic orbitals to generate a new set of molecular orbitals. And this new set of molecular orbitals can be based on unhybridized or they can be based on hybridized. And so we'll get sigma and then pi, etc. We'll have sigma star, pi star. And so it's a whole new set of orbitals that we would learn if we take the molecular orbital approach. For this lab, we're going to use the valence bond theory and generate drawings like this. So in valence bond theory, we're not going to worry about molecular orbitals. We're just looking at atomic orbitals, and we want to know all the atomic orbitals, and we want to know how they interact and how they fill with electrons. So here's a little animation video on hybrid orbitals. There are lots of YouTube animations. Actually, can you see this on the lower right? It's hard to see. I'll go full screen if I can.
Hybrid orbitals are formed by a mixing of a...
Here are the three p orbitals that are unhybridized. And when I was asking about the angle between the p's are 90 degrees. They're all orthogonal to each other. And so this is a set of orbitals, three orbitals that are 90 degrees in relative orientation to one another.
The hydrogen-like s, p, and d orbitals that characterize a free atom. The three p orbitals are directed along the x, y, and z axes. When we mix an s and a px orbital, we produce two hybrid orbitals called sp, pointed in opposite directions along the x-axis. Mixing...
It's important. This looks like a p orbital, doesn't it? Yeah. But it's not. This is a p orbital would be one single orbital with two lobes. This is two separate orbitals. So this is an sp orbital here on the left, and this is an sp orbital on the right. And so those are two separate orbitals versus one big p orbital.
Pointed in opposite directions along the x-axis. Mixing of an s with the px and py orbitals produces three equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes, which contain most of the electron density in the orbital. These are used in bonding to other atoms. Mixing of the s with all three p orbitals results in formation of four equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron.
All right, so these are our four sp3, except they're showing the minor lobe. It's a mix of S and P, so it still retains some of the P character. That is, it has two lobes, but they're lopsided. There's one big one and one small one. So what most people do is they ignore the small one and then just look at the big one. And so we'll have four sp3 orbitals. Here's 1, 2, 3, 4 in a tetrahedral arrangement. And then all these minor lobes are ignored.
Let's apply the concept of hybridization to ammonia. Here is the Lewis structure for ammonia. There are 4 electron pairs in the nitrogen valence orbitals. We know that an ammonia molecule has a pyramidal shape. This shape can be explained by assuming that the central nitrogen atom employs sp3 hybrid orbitals. The unshared electron pair occupies the 4th sp3 hybrid orbital. Hybrid orbitals are formed by an
So we want to be able to draw all the hybrid orbitals. So let's start off with that here. So the first thing is we aren't going to have any hybrid orbitals in the first shell. There's no 1p orbitals here. So it's going to start off in the second shell, third shell, fourth shell. You know, they all have p orbitals that we can hybridize with the s. So if we take an s and one of the p's, so I can draw an s orbital like this, and then one of the p's, we'll draw the px like this. Okay, that's going to leave a py here and a pz that are going to be unhybridized. So we'll draw those like this. And so when we hybridize that, we're going to get the sp hybrid orbitals. The sp hybrid orbitals will have one big lobe. Now, we're not going to show the minor lobe here. So there is a minor lobe. Oh, I'll show it this time, but normally we don't show that. And so here's another sp. And so this is taking the p, which is one dumbbell, and this s, which is a spherical, and then making 2 sps, like this. The unhybridized p, okay, so there'll be a p here and a p here, are not affected. So that's p, p. And so when we draw the orbital energy level diagram, we'll have the 1s, which I didn't draw in here, but it's untouched. And then 2 sp orbitals, which are going to be halfway between the s and the p here. So this will be an sp, this will be an sp. And then 2 unhybridized p orbitals here, here. And those unhybridized p orbitals I'm trying to show in purple down here. And so this is sp hybridization. And then we're going to have sp2 hybridization. sp2 hybridization is going to start in the second and or the third or the fourth. We need orbitals with similar spatial proximity. So, for example, I can't take the 1s and hybridize it with a 2p. They're too different in terms of the radial distribution. So if I take an s orbital here, and one of the p's, let's say, and another of the p's, so we'll take the px and the py. And what that's going to leave is it's going to leave an unhybridized p. The unhybridized p we'll just put perpendicular here. So this is what I call a top view. We're looking down here. And then when we hybridize those, it's going to look like this. This is going to be an sp2 hybrid orbital here. And then we'll have another one here and another one here. And this is going to be an trigonal planar arrangement. And that leaves the p orbital here. And so one lobe of the p orbital is sticking out, the other is sticking in. So that's going to be the p. So this one I call the top view. I also have a side view. drawing for this. And for the side view, I'll just rotate it from this sp2 here. If I do that, I'll have an sp2 here, but this sp2 is going to come out of the plane now. And so I'll have one sp2 out, and then I'll put one sp2 that comes into the plane here. So those are my three sp2 orbitals. I didn't draw the minor lobes on these because it's going to get too messy. And then I'll draw the p orbital in here, which is this dumbbell shape p. That's just one p orbital here. And so this one is the top over here. This one will be the side view. It's side view so we can see the p orbital in profile. The energy level diagram is going to be 1s, and then we're going to have our three sp2 orbitals, and then our one unhybridized p orbital, which is shown in purple there. But we get our three equivalent sp2 orbitals. So this is sp2. And then for sp3, since we just did ammonia, it's going to be pretty much that. We'll have the 1s, the 2s, the 2p, but in this case, there are going to be 0 unhybridized p. All the unhybridized p orbitals we're going to hybridize. And so we have our s, our px, our py, and our pz all hybridizing. And when we do that, we're going to get 4 equivalent orbitals in a tetrahedral geometry. This will be it. And the way it's going to look on the energy level diagram is we'll have our 1s and then our 4 sp3s. Since n is equal to 2, I'll call it 2 here. All right, then we fill them up with electrons. When we fill them with electrons, though, we have to pay attention to formal charge. You know, and in order to pay attention to formal charge, we look at the Lewis structure. We also have to pay attention to multiple bonds, like double bonds, like in CO2 that we did the other day. All right, so you're just going to work on this. So I would do ammonium and then amide, so you get a better feeling what to do about formal charge and valence, the number of valence electrons. The other thing we have to be careful is, you know, when you're talking to people about the electrons, like a nitrogen, how many electrons does nitrogen have? Well, it has 7 electrons, but that's 7 total electrons. So if you're looking at total electrons, you're looking at whole shells. Or has 5 valence electrons. If you're looking at valence electrons, you're just looking at the outermost shell or the highest n orbitals. You know, there are different n's on there. And so be careful with that as well. All right, are there any questions? This?
So for the, since it's an ion, it's post, does that mean one electron is missing?
One electron's missing, right? There are 2 ways of handling that. One is by using the rules. The rule for Lewis structure is you sum up the total valence electrons, and then you add an electron if it's negative, you subtract an electron if it's positive, or you just leave it as if it's neutral. That's one way. The other way of figuring out how many valence electrons is by looking at the formal charge. You know, the formal charge will tell you. If there's no formal charge, then there's no extra electrons, and it's not missing any electrons. It just has the correct number of valence electrons. Okay, other questions? All right, why don't you work on these? You could work together, but I'd like to check them off as you go along. So after you finish one, finish one means draw the unhybridized, fill it with the valence and core electrons, then move on to the hybridized. And then you're going to show me how things bond like we did with ammonia.
All right, I'll stop talking here and then you can work on this.